Hello everyone and welcome to this video, and today we are going to talk about databases and concurrent transactions in them. See, databases need concurrency, and with concurrency comes some problems. And today we will see some solutions to these problems. See, in databases there are multiple transactions trying to access the same piece of data using multiple threads. And it's the responsibility of the database to see that this data gets modified properly. And what do I mean by properly? For many databases, it means it adheres to the ACID properties. And I hope you know about them, but here's a refresher. See, ACID means atomicity, consistency, isolation, and durability. So let me give you some lines about them, but you can, if you want, you can read more about it from elsewhere. Because this is some database fundamentals you should really know about before understanding this topic, right? So ACID, from that, atomicity means transactions are either completely succeeded or completely aborted. So it should not happen that a transaction goes half the way and it updates some values it needs to update, but not all the values. It should not happen like that. It should completely succeed or it should completely be aborted and roll back, right? Then next comes consistency. What does this mean, right? It means that some value, let's say in a database like a column's value in a table, cannot go below 0, which is a database rule. Consistency says that our data should adhere to these rules when a transaction goes over them, right? So we can generally say that it means that if the database was in a consistent state before the transaction starting, it should be in a consistent state after the transaction has completed it. So the transaction needs to, the database needs to make sure that the transaction does not change the data in any way that it does not follow the rules of the database, right? Next comes isolation. What does this mean? See, it means that even if multiple transactions modify the same data, the transaction should act completely independent of each other. So it means that even though two transactions are running at the same time, it should appear that the transaction has run one after the other. So it, like what I've written here, is transactions that run concurrently appear to be serialized, like a formal way to say that. Now, one thing is that isolation in many cases is not strictly enforced just to keep these operations faster, but that is a entire different rabbit hole, and maybe we'll do a separate video for that. And then comes durability. It's a simple thing. It means that something that let's say if any transaction commits something to the database, it should be saved and the data should be persisted, and even if the database restart, the data should be there. So all that data should be persisted properly, and nothing should come and undo those changes unless there is a new transaction to make those changes again, right? So it makes sure that the data in the database is safe and it will not just go away someday and you will not find your data anymore, right? Okay, now with ACID in mind, let's see the troubles we can get ourselves into when multiple transactions take place at the same time. See, when two transactions are running at the same time and both of them are read transactions, we don't have any problem because no one is modifying the data. The order in which those read operations goes on is immaterial, right? But the problem comes when one of the transactions is a write transaction, right? Because then some transaction and some operation is modifying the data and the other one is trying to read it and maybe change it too, and then there is some problems. So we will see what those problems are before solving them. Okay, so this is a first problem that we're gonna take a look at. This is called a read-write conflict or an unrepeatable read, right? First, let me tell you a bit about this notation. So what do I mean by RA? This means I'm reading some database object called A. And what do I mean by a database object? It can be, you can think about it like a value in some column of some table in a database. But don't, like, why I'm abstracting it out to a database object, because it can be anything. Not all databases have tables. Some databases have documents and graphs and all the other things. So like this A or B, whatever I'll say, this database object can be anything in a database that can be read or written, right? So it's any piece of data, right? So what we're doing here is reading A, and then there is this new transaction called T2. So this is transaction T1, this is transaction T2. What it is doing, it's reading A and then writing some value to it. So let's say A's value was initially 0. This RA in T1 reads it 0. Then T2 comes, reads it as 0, and then changes the value to 2. Then when T1 does RA again or read A again, it reads 2. So in the same transactions, there are two read operations and they're reading different values. This is a problem, and this is called the read-write conflict or the unrepeatable read, right? Let's go to the next problem that can happen, right? So this is called the write-read conflict or the dirty read. So what happens here? Let's see. Let's say a transaction writes something and then the other transaction reads that value, right? So this can happen anytime. Let's say they write A's value to be 2 and T2 reads the same value, but then the first transaction aborts. So dirty reads means that a transaction reads some data that was never meant to be committed in the database, right? So because this transaction has committed, let's say A's value was 0, and in the beginning of both the transactions, T1 comes, it changes the value to 2, right? T2 reads this value and does its operations according to it, but then when it aborts, the value is rolled back again to 0. So T2 has read some ghost value out of nowhere and it will mess up all its operations, right? So this is a dirty read because it's reading some garbage value which will never be persisted in the database, right? Let's go to the next one. So this is a write-write conflict. Let's see what's happening here. This is an interesting one. So we have two transactions. The first transactions writes A's value to be 10. So A is currently equal to 10. Then transaction T2 comes, changes A's value to 9 and sets B's value to 0. Then transaction T1 comes again and changes B's value to 2. Now what's the problem here? You see, A's value comes from T2 and B's value comes from T1. This is a problem because our transactions should either succeed fully or not succeed at all. So let's say the proper values for this should either be 9, 0. So A equals to 9, B equals to 0, or A equals to 10, B equals to 2. So either T1 should run first completely or T2 should run first completely, right? Let's say T1 would have run first. The values would have been written to 10 to A and B. And then T2 would have modified the values to 9 and 0, right? But this is not what's happening here. One value is coming from T2 and one value is coming from T1. So which transaction actually took place first, right? That we do not know. And this is the problems that we are trying to solve. So you see in here with this write-write conflict, I was talking a lot about this. It looks as if these transactions ran simultaneously and not one after the other. But that should be our goal, to create schedules or, this order of these operations so that it looks as if the transactions took place one after the other, even if they took place at the same time, right? So this is called a conflict serializable schedule. It means that either T1 ran before T2 or T2 ran before T1. We cannot determine in a database that whether T1 should have run first or T2 should have run first, but our database can guarantee that one transaction runs first of the other transaction. In reality, it might be running together, but it should seem to the user, it should seem seeing the data that one transaction has run before the other and one transaction has completed completely, it has succeeded fully, then the other transaction has taken place, right? So if you see, we are writing two values here and then T2 is coming and overriding these two values. So A and B are both coming from T2. So T1 has completely taken first, and then T2 has overridden its value. So one after the other, right? This is a conflict serializable schedule because both the transaction has completed as they should, and there is no mixing and matching of values from one transaction and the other transaction, right? Let's go and see how can we solve this problem. See, one thing we can do is something like this, where we just say that two transactions will not run at the same time. There will just one transaction running. That will solve our problem, but that will just make our database slow, like stupidly slow. We don't want that. So it's obvious that we'll have to interleave our operations. And what do I mean by interleaving? That means, let's say one transaction does a write, the other transaction will do a read. So it's not that one transaction will complete, then the other transaction will start. It means that both the transactions will run at the same time, and their operations will be interleaved. But how do we make it seem that the transactions have run one after the other? That's the problem. We want conflict serializable schedules. How can we do this? Now, one strategy that can come to your mind is locks, right? What do I mean by that? If our transactions are able to say, okay, I want a lock on A. What does it mean by that? It means that it will not let, the database will not let any other transaction to read or write to A at this time. This is how the database, the two transactions parallelly can do operations on different objects at the same time, but not at the same object. So if another transaction wants the access to A, it will have to wait till this transaction is done. But what should be a locking strategy is the question. See, let's talk about this example. There are two transactions. T1 says, I want a lock on A, then changes the value and unlocks A, which is fine with our current algorithms. Then T2 says, okay, I want a lock on A and B, then changes these two values and then unlocks A and B again. It's fine. Then T1 again easily gets a lock to B, fine, and changes the value of B and unlocks B. This is allowed in whatever we discussed right now, right? Because they are taking locks, so it should be fine. When they are changing the data, other transaction cannot change this data. But we are land with a same write-write conflict. One value is coming from one transaction, the other value is coming from the other transaction. This should not be happening. It should either have been 9-0 as I said, or 10-2, right? So we are not getting a conflict serializable schedule even if we are using locks. So that means we cannot use locks mindlessly. We need to have a specified algorithms to tell the transactions when it can have locks and when it cannot have locks. And this is where two-phase locking comes in. See, what is happening here, the problem with these two transactions is that A is changing some piece of data and then it's letting other transactions to run free. So T2 comes in and does all the changes it needs to do. And then T1 says that, okay, I need another lock on B and change the data. So you see, it's not like telling in advance all the values it wants to change, if that makes sense. And this is causing confusion because the other transactions will not know that when it will change which object, and that makes it problematic. So here it comes two-phase locking. So let's see what it does. See, two-phase locking has, well, two phases. That should have been obvious. It has this growing phase and it has this shrinking phase. So what does these two phases mean? It means that our transactions can start taking locks. Let's say it takes lock on A, lock on B, does some operations and takes a lock on C. But once it releases any lock, so let's say it says unlock B, then it will not be able to take any more locks. So now I say that, okay, let me do a, let me continue from here to here. and let's say it says log B, sorry, let's say log D again, it cannot do something like that. This is not permitted. Once it has unlocked a lock, it can only release locks. It cannot ask for more locks, and it goes into the shrinking phase. So in growing phase, the transaction collects all locks, and in the shrinking phase, the transaction leaves all locks. So this is the algorithm that we are going to follow, and let's see how it solves our problems. Okay, so here is the same write-write conflict problem that we had. Now see, following two-phase locking, we're taking two locks and changing a. T2 has asked for these locks too, but it now has to wait till T1 has done. So now it will take, now it will change 10 and 2, A and B. T2 is still waiting. Then at the end it unlocks B and A. After unlocking B, it cannot, it's so last time what it was doing, it was taking a lock at A, then unlocking A, then taking a lock at B, then unlocking B. It cannot do it here. It has to take locks, and then when it unlocks, it can only unlock. It cannot ask for more locks, right? So then it has done unlock A and unlock B. Once it has done unlock A and unlock B, T2 gets access to these objects, right? So now it writes 9 here and 0 here, then it unlocks. So now you see both the values are coming in from T2. That means one transaction seems that it has run before the other transaction, right? Now in this particular example, the operations have kind of happened like that only, that one's operation has finished, then the other's operations have begun. But it's not always that it will happen like this. The transaction may, like the operations may go on at the same time also. Let's see in this example, you can understand this better. Okay. First, T1 asks for lock A, T2 also asks for lock A, but let's say T1 has asked maybe a few seconds earlier, so it was given to T1, right? Then it has to wait. T1 also asks for the lock of B, and it changes the value of A, right? And it unlocks A. After unlocking A, it cannot get any more locks, right? Once it unlocks A, T2 gets the lock to A. So let's say A's initial value was -1, B's initial value was also -1. A's value here was changed to 10. Then T2 came in this place and changed the value to 9, right? Now T1, because this has a lock to B, so T1 writes the value of B to 10, and T2 asks for the lock, but now it has to wait, right? At the end, it unlocks B and it commits. Cool. So it the T1 has completed and committed. T2 is still going on. T2 now gets the lock to B because T1 has unlocked it. It changes the value from 10 to 0 and then unlocks both the locks. So you see that and final value is 90, which is something that we want. Both values have come from T2, and it seems like T1 has run before T2, which gives us a conflict serializable schedule maintaining database isolation, transaction isolations in the database. So this is the beauty, guys. You see it looks like T1 has run before T2, but in reality, it's not so. It is doing operations at the same time. So when it's writing, T1 is writing to B, T2 is writing to A. So this is making our transactions go faster, but it is not, it looks like it has, T2 has run after T1. This is the thing that we wanted to achieve, and we have achieved it using two-phase lock. But see, nothing in computer science is perfect, and this has some problems too. One of those problems is called the cascading aborts, right? What does it mean? See, let's say some transaction is going on like this, right? T1 locks A, and then it makes some changes to A, and then it unlocks A, right? This is allowed by two-phase locking. This is absolutely fine, right? A's value is 10. T2 then obtains a lock to A, which is also fine, and then reads A. So T2 reads the value of A as 10. This is also fine. But then T1 aborts. Now T2 has a dirty read. You see this 10 that it has read, it is not committed to the database. So it's coming from the heavens for it. So we are getting a dirty read, and this is not solving our problem. That's why this T2 also has to be aborted. Right? So because T1 got aborted, T2, there was nothing wrong with this transaction. It has to also abort. Now this problem is called the cascading abort problem to prevent dirty reads. So you see that two-phase locking, even though it's really good, it is having problems of cascading aborts and dirty reads. To prevent dirty reads, we are doing cascading abort. But we need to solve these two problems. To solve these two problems, we have the strict two-phase locking. What does it mean? See, in normal two-phase locking, once I read take all the locks, then I can keep on unlocking locks, right? In strict two-phase locking, we cannot, after getting all the locks, we have to keep it till the end of the transaction, right? At the end, we can release all the locks. This is what makes it different, right? Only after the transaction ends, actually the locks will be released. So you see what's happening here. Locks are being taken, then it's writing 2 and 10 to A and B, and then this transaction T2 is also reading these values 2 and 10, then it unlocks and commits, then it also unlocks and commits. This is following strict two-phase locking because all the unlocks are at the end together with the commit. So when it commits, or let's say it aborts also, the locks will be given out. Let's see an example. So let's say this transaction T1 has written 2 and 10 to A and B. Let's say the initial values was A equals to 0 and B equals, let's say, 3. This has been changed to 2 and 10, right? Transaction T2 comes and gets the locks to it, and then T1 aborts. When T1 aborts, the these values are reverted back to 0 and 3. Now T2 gets to read this value as 0 and 3. Now why doesn't it read 2 and 10? Because till it aborted, the locks were with T1, so it cannot read it. It actually had to wait when it got these locks. So it waited till this transaction aborted, and when it aborted, the values were changed back to 0 and 3, and it got 0 and 3, and then it changed it, like unlocked A and B. Now you see, this gives us a completely serializable schedule every time. The problem, however, is this will make our queries go slower, because the transactions will have to wait some extra time till the other transactions completely completes to access those objects that it had accessed. This can be a trade-off. Like if you want dirty reads in a database, you can deal with it, then you can just turn this setting off. But if you don't want dirty reads, then you'll have to go with something like this when we're talking about two-phase locking, right? There is another problem, and this is the scarier one. See, whenever concurrency comes and whenever locks come, this little friend comes back to us, which is deadlocks, right? What is deadlock? So in deadlocks, you see that I'm the T1 transaction and T2 transaction. So the T1 transaction asking for a lock to A, the T2 transaction is asking a lock to B, and they get these locks. So it gets A, it gets B. Now T1 asks for B, but T2 has B. It cannot get it right now. The T2 has to release it first. Now T2 also asks for A now. It cannot get it because T1 has it. Now both the transactions are stuck and our database is dead. To solve this problem, there are many mechanisms. I don't want to really go in depth for those in this video, maybe a separate video for this, but let me give you some primers. Like you can do either like a detection for deadlock. So there is some background process which keeps on trying to detect deadlocks in transactions, and after it has detected, it kills a transaction, right? So what happens, you can create graphs known as wait for graphs, right? Wait for graphs. Sorry for this bad handwriting, guys. Okay, so let's say transaction T1 is waiting on transaction T2, and transaction T2 is waiting for transaction T1. So we can create a graph of which transaction is waiting on which transaction, and if there is a cycle in this graph, like a cycle like this, we have a deadlock. When we have a deadlock, the database can decide if it wants to kill a transaction and let the other transactions go through to break this cycle. So this sums up the basics of two-phase locking. Actually, a lot of talking points in this video was taken from 2 lectures of Carnegie Mellon University Database Group YouTube channel. I'll link those lectures in the description. You can also go through those. They're great videos, by the way. Okay, so this will be it for today. Bye and see you in the next video.